Can you hear me? Yes, excellent. So thanks, Joël, for the introduction. As he said, I was quite intimidated when I saw the list of speakers who all know what they talk about when they talk about reinforcement learning. I came to reinforcement learning about 2 years ago. But the idea is I might present some aspects of RL that are less common in the academic community, but which I think are just as interesting. So just a disclaimer, that's my own experience. That's how I did things when I was working on actual products. It turns out that it will be focused on online advertising because that's where I use reinforcement learning. What I present is not at all limited to that industry. And it's really a more general statement on how you can use reinforcement learning in the industry. So usually when you think about reinforcement learning, we think about two things. The first one, it's multi-step episodes. So there's this idea in reinforcement learning that you're going to take an action that's going to influence the state, and then you're going to take another action, and so you're going to take a sequence of actions, and you don't want to be too greedy because you don't just want to maximize the reward at the next step, you want to maximize the reward at the end of the episode. And so I'm assuming that's what most of the talks were about, whether it's Atari, Go, helicopters. There's another aspect to reinforcement learning, is the aspect of reward, evaluation, and maximization. So there's really an important bit in RL, which we usually define which reward we're interested in, and we try to maximize that reward. And it turns out that in this talk, it's really this aspect I'm going to focus on. So just to be clear, it's going to be an RL talk with episodes of length 1. Okay? So there's not going to be any sequence of actions I want to optimize. And really what I want to show you is that RL has much more to offer to the ML community and to the industry than just the multi-step episodes. So it's going to be a simple case, but a point of view, again, that few people have. So I mentioned online advertising. It's going to be a subpart of online advertising called retargeting. And again, it's advertising. It's probably boring to most of you. It's boring to me. But it offers some interesting challenges. So what's retargeting? Whenever a user browses the web, the user lands on a web page, and then potentially there will be ads displayed on that web page. And so how are these ads chosen? Well, the website contacts what we call an ad exchange, which is basically an organism that runs an auction. The ad exchange contacts all the people willing to display ads, and then there's an auction going on. Each competitor tells the ad exchange how much they're willing to bid for the right to display one specific ad, and then the highest bidder wins the right to display an ad. So at my previous company where this work was done, we were participating in about 20 billion auctions per day, and we're displaying from 2 to 3 billion ads per day. Okay? And again, there are plenty of interesting works on multiple auctions, but right now I'm assuming it's a single auction. So really, the state is what you know about the user, the web page, and your action is going to be how much you're willing to pay, how much you're willing to bid to display an ad on that web page. Okay. So just details of the auction. So that's what's called real-time bidding. And most of the time, and I'm not going to talk about the more complicated cases, it's what we call a second price auction. That means that everyone's bidding at the same time. The highest bidder wins the right to display an ad, but the highest bidder does not pay what they bid. They only pay what the second highest bidder bid. Okay? And that has many, many interesting properties, but the one we're concerned about today is that the optimal strategy for everyone is to bid the expected gain, which means that when a user lands on a web page, I have to predict how much, on average, I'm going to earn if I display an ad, and if that's 10 cents, that should be my optimal bid. Okay? It's a very simple strategy, and that's why we use this auction scheme. And so what is, when I said on average I'm going to earn 10 cents, what is the expected gain? It's how much I'm being paid every time there's a click on the ad. So I'm going to display an ad, let's say for Walmart. Walmart is going to pay me whenever there's a click. So that's a contract. And there's another aspect, which is what is the probability that the user will click on the ad? Of course, if the probability is low, then on average I'm going to be paid little, so I want to bid less. If the probability is high, I'm going to be paid more on average, so I want to bid more. And this probability of click is something we don't know, and that's something we want to estimate. That's very old, and when people realized that that was the optimal strategy, there was a whole lot of literature on how do you estimate the probability of click. And right now, maybe some of you are wondering, where's the RL coming? And right now, there's absolutely no reinforcement learning, and this whole field wasn't using any reinforcement learning at all. And I want to show you that they were wrong in this. So again, you want to find a bidding strategy. You want to estimate the probability that there's going to be a click. So what you have is, in the past, you bid in previous auctions. Some of these auctions you lost, so you don't know what happened, but some of these auctions you won. And so you got to display an ad, and you got to notice if there was a click or not. And so you have access to a labeled data set, okay? With some idea, X is information about the user, the web page, and Y is a binary label, click or no click. And whenever I show this, the first reaction to people say, oh, that's easy then. I have access to data. I don't know how many of you were in the deep learning summer school, but it's really a supervised learning approach, which is, oh, I have access to labeled data. I want to predict the probability of Y equals 1 given X. I'm going to build a classifier to do that. And you're going to have a lot of research and people very excited, and they want to design new models, and you're going to have deep models to better predict this probability of click. Once you've done this offline, so you've carefully constructed your model, you have a good model, so you followed your machine learning classes, you have your trainer, your test, and you computed on test, and you saw that your model does better on the test than the current model, then you're going to go into production. That has a cost, so you involve a lot of engineers, you A/B test your solution. That means that what you're going to do is we're going to split the users into two. Some of them will have the current production system, some of them will have your modification. We wait for a few days, and in the end, we check which system brought the most money. All's good and dandy until you realize that these are the results you get. So on the x-axis, you have the offline test performance. On the y-axis, you have how much money did your system actually bring. And you can see that the correlation is actually really, really low. So there is no guarantee that the better system you have will indeed bring more money. And that's extremely important because everything we do in machine learning, the only thing we hear is that we should care about the test error and that the better test error is actually something we want to achieve. It turns out that in these situations, you can have a better test error that doesn't do anything for the actual problem you're trying to solve. And now I'm trying to explain how reinforcement learning can help in these situations. And that's really not a random occurrence. That happens all the time. So usually what happens when you start a company is at first your model is so bad that everything you do does better. And so you have a good correlation between test error and revenue. You're super happy and you keep going. And on a past company, this lasted for a few years. And at some point, the correlation starts to decrease and people start to get a bit uncomfortable with this. And the solution most of the companies do is, let's try more things, but that has a cost. And so I'm going to give you a principled way of doing things, again, which I think is really important. So why do we have this discrepancy? There are two implicit assumptions we made when we assumed that the test error, so I said RMSE here, but the log loss would be about the same. There are two implicit assumptions we made when you said the test error is relevant for what we want to do. The first one is we said, oh, I'm using the log loss, so the test log loss, that's going to be a good proxy for the revenue. If I make a better log loss, I'm going to make a better proxy for, that means I'm going to make more revenue. The other assumptions, and that, again, that might be something you're more familiar with because that's really the topic of this summer school, is that we assumed that the input distribution was the same. Okay, that's really, again, the assumption we make is that the P of X on the train set and P of X on the test set are the same, and so that's why it makes sense to focus on the test error. And what we'll see is that in many real-life scenarios, that's really not the case. And what you do influences the input distribution, and so what you do in these cases. And it might seem obvious to you in this particular setting, when you're in a company, people usually discard this problem. They say, machine learning only taught me how to deal with the same input for distribution for train and test, and so I'm going to make the assumption even though it's wrong. Okay? So just to give you a quick idea, I'm going to do something I've never done before, and I was told by many people that was a bad thing to try, but I'm going to try. I'm going to do a quick demo on the board of why this is a bad idea. So hopefully you can all see the board. I don't know if there's some light that needs to be turned on. But let's assume that there's a user that on average clicks 20% of the time. So CTR is called click-through rate, is the probability that they're going to click. So on average, a user clicks 20% of the time. Now, your model is going to predict a click probability, okay, which I'm going to call, let's say, P. And what does the log loss say? Well, the log loss tells you that the loss you incur for P is going to be equal to minus 0.2 times log P minus 0.8 times log 1 minus P. Hopefully, I'm not teaching you anything new right now. And so if the probability you have here, you have 0 here, you have 1 here, your loss looks something like this. Okay? With a minimum at 0.2. And there's really a problem that it's not too present in the RL community, but it's present in pretty much everywhere else in machine learning, and no one mentions it. Is you're going to see many papers where people define the loss function. And the way they justify this loss function is they say, the optimum of this loss function is what I want. They only care about the optimum. They never care about what's outside. So here they say, oh, I actually want to predict 0.2. I have a loss where the minimum is at 0.2. That's fine, I'm happy. Now let's see what the actual loss is. So what I want to maximize is my revenue. So it's how much, or let's say how much money I'm making. So my gain minus how much I'm paying. Okay? The CTR is 0.2. So if I'm winning that display, I'm going to earn 0.2 minus what I paid in the auction. If I'm not winning the display, 0 will happen. And now, first, there's something you realize here that's really important, is that this depends on what the other people in the auction do. Okay? If you're by yourself in the auction, no matter what you predict, you're going to pay a price of 0 because it's a second price auction, and you're going to win the display. So it doesn't really matter. If, on the other hand, the competition is fierce, then it's going to make a difference. And so I'm going to make a very simple assumption. I'm going to assume my competitor bid from a uniform distribution between 0.1 and 0.3. So on average, they do well. And what's going to happen, I'm not going to do all the math, is that your loss, so I'm going to put loss here, so I want to minimize that. Your loss is going to do something like this. It's going to do that, 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 with 0.1 here, and 0.3 here, and 0.2 here. So really what this says is, if you bid lower than 0.1, you're not going to win anything. So you just, doesn't matter whether you bid 0 or 0.1, that's the same. If you bid more than 0.3, it doesn't matter. In here, it makes a difference. But you can see that this curve is vastly, vastly different from that curve. Okay. And again, it might seem like a minor point, but I really want to emphasize that you should not define a loss function just by its optimum. Because there are many, many loss functions that have the same optimum. And you should really define a loss function by considering how much do I pay if I make the wrong decisions. And the log loss, it might have nice theoretical properties. It's usually completely decorrelated from what you actually pay if you make the wrong decisions. Okay? So it's really important to think about this. So, but that's difficult because when I told you that I want to predict the CTR, you may know nothing about online advertising. You may know nothing about how the auctions are run. You don't care. You train, let's say, the logistic regression, and you come up with a model. Here, that requires to know a lot more. You need to know how your competitors are bidding, what's the kind of the auction. And so you need to have more knowledge, but in the end, that's what really matters. So really, just this small demo, the point is that if you want to have a system that's actually going to be used in real life, you have to know about what's happening everywhere else, and that needs to be included in your loss. And really, hopefully you see where this is going. This depends on the rewards. This depends on how much do I earn if I take the right decision. And so at some point, we need to talk about rewards. And that's what I said on the first slide. What I really like about reinforcement learning, much more than the multi-step episodes, which is nice, is that they actually talk about rewards. They're minimizing if the reward is an amount in dollars. Okay? It's how much money I'm making or I'm losing if I take this decision. It's not a log loss. So it might be less comfortable, but it's actually much more relevant to what you're actually trying to do. Now, the second point, which is another very important point, is the input distribution the same? So as I said, the data you have is on the auctions you won in the past. Okay, so on the auctions I lost, I don't know if there was a click or no click, so I can't learn anything on these things. But on the auctions I won, I know if there's a click or no click. The problem is the algorithm I put in production influences which auctions are won. So I have a past data of auctions I've won and clicks or no clicks. I'm going to try my new system. That's going to influence which input distribution I have. And now, how do I pick the system? Should I pick the one that works best on the current input distribution, on the input distribution to come? That's, again, to me, a complicated question, which RL can answer very nicely. So how many of you are familiar with Simpson's paradox? Okay. I think it's rarely taught. That's the source of, I'd say, 90% of the wrong decisions I've seen made by data scientists in the industry. So here's what happens. Now you're not bidding. You're trying to decide, let's say you're Google or Microsoft, and you're trying to decide if you want to display an ad on the top of the results or on the side of the results. And so what you do is, well, you look at past data, and what you see is that, on the top, you reach a click-through rate. Does that actually work? No, it doesn't. Doesn't matter. So you can see that on the top, you reach a click-through rate of 0.67%, and on the side, you reach a click-through rate of 0.71%. And so your natural conclusion will be, then we should actually put more ads on the side because they click more. Okay? It turns out that that's not the whole of the story. Because if you split by users, maybe for high-value users, so there's a way to detect which users are more likely to click. Maybe for these users, you really wanted to display an ad on top, but since your competitors knew they were high value, they displayed it on top. And so the only choice you had was to display them on the side. And so you see that for high value users, the top banner clicks more than the side banner, 0.6% versus 0.2%. And for low value users, the top banner also works better than the side banner, 1.2% versus 0.8%. So really, the conclusion is that the top banner is better than the side banner, but it turns out that because you weren't winning the top banner enough for the high-value users, you came to the wrong conclusion. An alternative may be, let's say, it's in medicine, you want to do cancer treatment, and you have either a very simple pill, which doesn't work that well, but at least it's not invasive, or you can do chemotherapy, which is much more complicated, but tends to be more effective. And then people could look at the death rates of these two treatments and say, wait, many more people die when they have chemotherapy than when they have the pill, so chemotherapy doesn't work as well. Whereas the reality is that no, they die more because you use chemotherapy in the hard cases. And that's obvious in that setting. In that other setting, that's really not obvious. So you can very quickly draw wrong conclusions from your past data if you don't do this. What's even worse is that, now let's assume you want to build a model to predict the CTR. When you're going to build a better model, so you're in that setting, you don't know about high value and low value users, so you're going to build a better model, you're going to build a Deepnet because that's what you've been told works. So you build a Deepnet, you predict the CTR better, that's going to make you display even more on the side banner, which is even more of a bad decision. So that's outside of the realm of standard supervised learning and standard machine learning, that sometimes you really do not want to just improve your tester. So these are called confounding variables. The high value users, the low value users, is the standard correlation does not imply causation. So how do you deal with confounding variables? And that's where RL comes in. One, which is usually done, let's say, by economists or in social science, it's to add as many variables as possible in a model. So you call that controlling for confounding variables. So you basically want to make sure that you're not forgetting any of these causes. That's usually complicated. Another one, which is what many companies do, is they run online A/B tests. Since the two errors, the one you measured on the test set and the actual error are decorrelated, I'm just going to do all my tests online. So whenever someone has a new idea, I'm going to put it in production, run it for a few days, see what works best, and do this. That's appealing. The problem is, if you're a smaller company, it takes longer for you to get the data than a bigger company. And so your improvement is going to be slower. And so eventually, you're not going to have the same pace of progress as bigger companies, and you'll die. So it's really important that you can keep the pace of progress and you can evaluate as much as possible online. Now, there's usually a remark that people do is that it's an exploration issue. Okay? Here, the reason is, oh, well, if I had displayed high-value users on top banner more, I would have realized that top banner clicks more, and so I wouldn't have made that mistake. So if you just take some of your data to do some exploration, you'll converge to the good solution. That's a typical bandit problem with exploit. I know how that works. I know how that converges. Is there something to? Yes. And so what I'm going to show now is something that took me quite a while to realize, and I don't think I ever saw mentioned in bandit papers, which is basically why in most cases bandit algorithms don't work. So here's the thing. I told you that the best thing you could do was to predict the CTR. And now the question that arose is, on which input distribution do you compute your CTR? Because maybe you're going to have some input distribution, you compute the average CTR, you're going to use this to bid, you're going to end up with another input distribution, you're going to get another CTR. Where does that converge? And what I'm going to show you now is that it converges to a solution which has nothing to do with the actual optimal solution. It converges to somewhere random, no matter how much exploration you put. So it's really not a matter of the amount of exploration. And now we're going to try to understand why in some cases it works and why in some cases it doesn't. So I'm going to go again with high value users. And so let's say high value users represent 50% of my users. And they click all the time. They're really nice. They love clicking. Now there are low value users. So obviously this is not a judgment on the people, it's just for me as a company. 50% of the users as well, but they only click 10% of the time. Okay? But now there needs to be a question of which auctions do I win and which auctions do I lose. So I need to include competitors. Okay? So I'm going to have my competitors, and since I'm a new company, I cannot distinguish between high-value users and low-value users, but they can. So they're going to bid differently for high-value users and low-value users. So for high-value users, my competitors are going to bid uniformly at random between 0.5 and 1. And for low-value users, they're going to bid uniformly at random between 0 and 0.5. Okay, so they bid less for low-value users than for high-value users, but I have a poor system, I cannot distinguish between the two, I'm going to bid the same thing for everyone. Now, here's the thing. If my bid is less than 0.5, I'm only going to see low-value users, so I'm only going to have a CTR of 0, I'm only going to observe a CTR of 0.1. Okay, so observed CTR and that's going to be my bid here. If my bid is less than 0.5, I'm only going to observe a CTR of 0.1. Now, if my bid is more, and I'm not going to go into all the details, if I bid 1, 1 is super high exploration. I win all the displays, I see everything. Well, if you bid 1, you see everything, and so you're going to see a mix of these two, and so your CTR, the average CTR that you're going to observe is 0.55. Okay? It's the average of 0.1 and 1. So now, what do? Well, you say, oh, I'm going to start by do full exploration. So I'm going to bid 1, I'm going to win all the displays. Good. I've seen that my average CTR is 0.55. Theory tells me that I should bid my average CTR. That's what performs the best. So now, given this, I'm going to bid 0.55. And now the average CTR you observe is slightly over 0.1. And so you're going to bid slightly over 0.1. And you're going to observe a CTR of 0.1, and you're going to converge to bidding 0.1. Okay? So if you run a bandit algorithm with full exploration, and every single time, so you start by buying everything, and you bid then the average CTR you observed, your CTR is going to decrease in this particular example and converge at 0.1. Whereas if I actually draw how much money you're making, so that's money, so I want this to go up, and that's my bid. What's going to happen is that between 0 and 0.5, you only see low-value users, and so indeed bidding 0.1 is the best strategy, and you can actually see that your gain is this, like this, with a maximum at 0.1. But then, if you bid slightly more than 0.5, you start winning high-value users, which bring you a money of 1, whereas you only pay 0.5. And now what's going to happen is the gain is going to be like this. And this gain is going to be much higher than that gain. I really don't want to make this too tedious. I really wanted to go into the minimal amount of details just to show you that even if the theory tells you, oh, my best bid is to predict my average click-through rate, on which data set do I estimate my average click-through rate? The standard belief from people who know about the bandit literature is to say the bigger data set, the better. And so if I buy everything and compute the average CTR over my entire population, this is going to give me the correct answer. And that's not the case. That's really, really not the case. So why is that true? Is that if you look at the bandit literature, so the bandit literature, as far as I know, originated with the multi-armed bandit, where you have a finite number of arms, and you try to estimate the average reward for each arm. That is fine, because that means your model is well specified. Each arm has a different reward, and you try to estimate each reward. That's good. In settings when you have many, many arms, or in my case, technically I have infinitely many arms because I have to bid the continuous values, there are two ways. Either you treat this as a multi-arm bandit, where you say, let's say I'm going to divide this into 100 and I'm going to estimate the expected reward over these 100 arms. That's usually not a suitable solution because you just have too many arms, it requires too many data. And so people invented what's called the contextual bandits. And so they say, rather than estimate, and that's Q-learning for you. When you do Q-learning, if you think about Q-learning with episodes of size 1, you're going to learn a Q function which is going to tell you for each action, what is my reward? Okay? That is fine, except there's something, again, that no one talks about, which is that if your Q function is, let's say, a Deepnet, when you try to update the Q function for an action, it updates the Q function for all the other actions as well, in some setting that you don't necessarily master. And what that means when you have this is that your Q function will try to be better for the actions you take often than for the actions you don't take often. In multi-arm bandit, this never happens, because in multi-arm bandit, you only update the reward of an arm when you draw that arm. So it's not influenced by what you do on the other arms. When you have contextual bandits or Q-learning, what you do with one action usually influences the answer you give on the other actions. When you do this, no matter how much exploration you do, you're not guaranteed that you're going to converge to the right solution. Because the solution you converge to depends on the input distribution you had. And I can give you E-greedy with 5% explorations, E-greedy with 10%, E-greedy with 20%. These are all going to be different data sets. If your model is well specified, all these data sets will converge to the same solution. If your model is not well specified, all these data sets will converge to different solutions. And your model in real life is never well specified. Again, except in the multi-armed bandit, which is the simplest case. When you have many, many actions or a continuous set of actions, your model is not well specified and you need to be extremely careful. And the way you can be careful is by controlling for the input distribution. And again, we'll see this. This is again reinforcement learning. So when your model is misspecified, it comes back to what I was saying with the cost function. You have trade-offs to make. You can't get a perfect answer in everything. And so you need to make sure that which trade-offs you're making. So the last possible thing you can do to try to evaluate the performance of a new system, as we said, exploration doesn't work. Running online A/B tests is very costly and was more likely than not your company will go down under. You want to ask what's called counterfactual questions. So really what you want to ask is, what would have happened if we had done something else? So my current system makes decisions in production, and whether it's a translation system or a bidding system, anything, it doesn't matter. Your current system makes decision, and now you come up with a new system, and you really want to answer the question, what would my new system have done, and would it have been better or worse than my current system? And it turns out that it looks like a complicated question, but that's exactly what importance sampling is and what reinforcement learning does. So your current system in production, what it does, it observes states and it takes actions with a certain probability p. And now you come up with a new system, which is really just a new distribution over actions given the states, which you call q, and you're asking, how will this perform? And I know you've seen this at least once, but you've probably seen this many times over the last 3 days. It is just to know the performance of a policy Q when you have collected data under a policy P. You can just use importance sampling, and that gives you, on average, the correct answer. Okay? And compared to what I've said and about exploration, really, what's extremely interesting about importance sampling is that it controls for the distribution with which you gather data. Okay? There's a P somewhere in my formula. So I have to know how you gather the data to make a correct decision. So when you do this, so that's what we did at my, again, previous company. Rather than say, oh, I'm going to compute the training error test error and then run an A/B test and see how that goes, I'm going to use importance sampling. And so P is the distribution with my current system, Q is my distribution with a new system, and R is the reward I observed. And since I want to maximize how much money I'm making minus how much I'm paying, that's the reward. And that's really so off policy, policy evaluation, and that's the kind of results we got. So on the x-axis, you have the estimated reward with a new system. On the y-axis, you have the actual reward when you run an online A/B test. And these are rectangles because you have confidence intervals. And now you can see that the correlation is much, much better. It's not perfect because, as you know, importance sampling has variance issues, and you may also end up with bias issues, but it's incredibly better. And so again, I really want to emphasize that point. What was time? Good. So I really want to emphasize that point. In an industry, you might care about performance, but at some point you're going to care about evaluation. And you need to provide tools to evaluate a new system quickly. Because every time you don't do this, that means you have to go to production. And usually the costs of going to production are much, much bigger than the cost of trying something with TensorFlow or Scikit-learn or any toolbox. So evaluation is underrated in companies. Proper evaluation is really underrated. And there's much more to evaluation than computing the test error. And again, RL offers a proper solution to this issue. But now that we can evaluate Q, well, we can also optimize over Q. And again, that's something you've seen several times, at least in Peter's talk on Monday. Now you can ask, well, what is the best new system I can do? And you really want to do optimization. But you have new constraints coming in. In our case, for instance, when your system is applied to 1 billion or 2 billion users, you really don't want to roll out a new policy like this. You want to have some constraints. And so you've seen many techniques like trust region policy optimization or a bunch of other techniques. Usually what these techniques do is they have a policy, they make a small gradient update to that policy, they roll out the new policy, gather samples, and do this over and over again. There are many cases where you can't do this because just creating a new policy and putting it in production can take a day or a week. And so what you want to do, you come up with another problem, which is really, I'm doing this because I'm trying to entice you to work on these problems. These are undertreated in the literature, which is how do you do policy learning when you have a constraint on how many policies you can try? Let's say, or you can think of this as, I want to do optimization. Usually people care about optimization at a matter of number of updates. Optimization versus CPU time, which makes a lot of sense, but sometimes optimization, like loss as a matter of number of updates, is important because doing an update is complicated. If you work in the nuclear industry, you can't make a parameter update every second. Okay? It's going to take a few days. So I think it's really the same when you do direct policy optimization. There's a whole field which is how do you optimize this by making few policy updates. There's another very strong benefit of policy evaluation besides being a better predictor of the performance, which is it predicts tangible quantities. And at my previous company, I was discussing with people in product. And you can come to them and say, oh, I've reduced the log loss by 10%. It means absolutely nothing to them. And if you say, oh, I can put the system in production, it reduces the test log loss by 10%, but it's going to require an extra $50,000 in machines, no one knows how to make that trade-off. When you apply the reinforcement learning language of rewards, now you don't have a log loss, you have an actual amount of dollars that you can predict. Okay? Here, on the x-axis, I have dollars. On the y-axis, I have dollars. They're the same quantity. So now you can answer a lot of important questions, which is, well, I can achieve this solution, or I can achieve this other solution with twice as many machines. Is this worth it? Well, no, I know because I know how much machines cost. I know how much better my solution is in dollars. I can make the trade-off. There's also other interesting things you can do, and we did. So I don't know how many of you are familiar with optimization, but there's this thing called constraint optimization. So sometimes you want to do optimization, but you want to add a constraint. And usually the constraint is, oh, I want the norm of my vector to be less than 1, which makes little sense, but that's what we usually do in optimization. Here, again, we can apply constraints on tangible quantities. Now you can say, I want to do policy optimization. I want to maximize the number of dollars I make, but I don't want to increase the number of ads I display by more than 10%. That's something you can evaluate. That's something you can optimize over. And it becomes a very simple language to communicate with other people. So again, this is underappreciated in the academic community because we usually don't necessarily build products or talk to other people who don't have the same incentives. But it's really important when you're in a company and you talk about log loss, very people know what that means. If you talk about dollars, it's much more tangible. And reinforcement learning, the reward part of reinforcement learning gives you a language to do this, and I think that's absolutely crucial. Another point which has not been treated much in the academic literature, I don't have necessarily a solution to this, which is that there are systems where you run optimization quickly. So my policy, I want to update my policy, but maybe the landscape is changing. Some competitors come, some competitors go, and so my optimal policy is going to change. So within my policy optimization, I have an optimization procedure, and most of the algorithms you saw, like TRPO, they have step sizes or constraint on the KL. And how to tune that step size is not necessarily completely obvious. If you only want to learn a policy once, that's absolutely fine. You can fine-tune this by hand. If you have to do this across the entire company many times per day, you can't do this by hand. So we need to come up with robust policy optimization procedure which do not need any hyperparameter or where the hyperparameters are the same across all situations. And robustness is sometimes talked about in papers, but I think not as much as it should be. And from experience in optimization, usually what makes that an optimization algorithm is used or not, it's not the raw convergence speed, it's how easy it is to adapt the parameters to your particular problem. And I think that's something we should focus on. I'm not going to go into detail, but I think there are, again, other unanswered questions which are really critical in the industry and not necessarily very much treated in the academic literature. Inference time is critical. So in many cases, you want to make decisions fast. In some other basically, you pay a price for making slower decisions. And so we need to come up with algorithms which can make a trade-off between precise inference or fast inference. Right now, we usually use the same system to do inference in all kinds of cases. That's suboptimal in many situations. The other one is rewards come under multiple form. As I said, in our case, we wanted clicks, but maybe we want sales, or maybe there are many other things we observe. How can we include all these kinds of rewards into our system? That's still an open question. So the quick summary is, in industry, robustness and efficiency are critical. And when I call about efficiency, it's not necessarily converging quickly, it's also pipeline efficiency. You want to be able to try new ideas quickly. You want to be able to discard bad ideas quickly. And to do this, you need to have a proper evaluation system. RL, in my own experience, offered me the best tools to have a good evaluation. It offered me tools that I hadn't seen in other machine learning settings. And so I think that's a really important use of reinforcement learning. Again, I'm not sure I can call this reinforcement learning since these are episodes of size 1, but I think it still offers the correct vocabulary to deal with these things, especially the idea of rewards, of actual rewards, which is usually not mentioned in supervised learning. Improving the model, many people care about improving the models, and you have many papers on how you make better models. That's usually, I call useless, that's big of an overstatement. That's usually much less important than knowing what you actually want to optimize. So the loss function, I think much more care should be put into the choice of loss function than what it's actually done. Usually you're going to have either the log loss or the mean squared error because that's what everyone has been doing. I think we should think a lot more about this. And again, it's not because a loss function has the correct optimum that it's a good loss function. A loss function gives you plenty of trade-offs, and you need to make sure that these reflect the actual trade-offs you're making. And as said, to me, the last real important aspect of reinforcement learning is that it deals with tangible quantities, physical quantities you know how to manipulate, and it makes a lot more sense. I don't know how to constrain the norm of my parameters. I don't know what's going to give the best results. I know how to constrain an amount of dollars or an amount of seconds. That's a lot easier. So thank you, and if you have any questions.